This is a multiple-choice question about the RationalQuadratic kernel, a function used in machine learning to model relationships between data points. I'll need to understand how changing its settings affects the model's behavior. This sets the stage. I'm going to evaluate several statements about how changing parameters in the RationalQuadratic kernel impacts model behavior and determine which are accurate. This section introduces the core concept, exploring how modifying parameters within the RationalQuadratic kernel influences results. This statement focuses on the parameter alpha. Lowering alpha makes the model more sensitive to nearby data points, less to distant ones. This statement talks about setting boundaries. The range of 1e5 to 1e5 means length_scale can take on extremely small and large values. That gives us flexibility in finding an optimal setting. This simply indicates that options A, B, C, and D are all potential answers to the multiple-choice question. This is the title for a diagram, not shown here, likely illustrating how the parameters affect the kernel. This question is the key starting point to test my understanding of the RationalQuadratic kernel within the scikit-learn library. The title for a graphic, likely showing the effect of each parameter on the overall kernel function's shape. It would be useful to see this diagram to visualize the concepts. I set the limits for the length scale parameter. Think of it like setting the minimum and maximum values a dial can reach. A wide range, like 1e5, 1e5, lets the model explore many different levels of smoothness. A small range restricts the possible smoothness levels. This is important because the length scale directly controls the model's smoothness. This parameter controls how smooth the model's predictions are. A larger length scale means points further apart influence each other more strongly, resulting in smoother curves. Think of it like this. A larger length scale is like using a wide brush for painting. You get smoother strokes. A smaller length scale is more like using a thin brush, resulting in more detail and less smoothing. Alpha governs how much the rational quadratic kernel behaves like other kernels. As alpha gets really big, the kernel acts just like a squared exponential kernel, another type of kernel used in machine learning. If alpha is small, it acts more like a Matern kernel, which emphasizes local data points more. It's like a switch. With a large alpha value, you get one type of smoothing, and with a small one, another. This is the main question driving our investigation. It's all about how we tune the parameters to get the best fitting model. The rational quadratic kernel is a special function that lets us model data in a flexible way. Its parameters control the overall shape of the model. Length scale sets smoothness, and alpha determines the balance between different kernel behaviors. I'm explaining the effects of changing parameters in the rational quadratic kernel, a function used in machine learning to model relationships between data points. It's like a flexible tool. We can tune it to fit different types of data. This question tests your understanding of how changes to the parameters impact the model's behavior, specifically in a rational quadratic kernel. This statement deals with the length_scale_bounds parameter. Think of length_scale as a dial controlling the smoothness of the curve, and length_scale_bounds defines the range of this dial, from 1e5 to 1e5. A larger range means you have more flexibility in adjusting the smoothness. So setting these bounds as 1e5, 1e5, provides this wide flexibility to tune the model. The alpha parameter is like a blending knob. A higher alpha value makes the rational quadratic kernel behave increasingly like a squared exponential kernel, which is a different, smoother kernel type. It's a way to smoothly transition between these types of models. Let's talk about the influence of alpha on local data points. As I decrease the value of alpha the model starts to emphasize nearby data points more. This is because the rational quadratic kernel then behaves more like a Matern kernel, which is known to be sensitive to local points. I'm focusing on length_scale. If I increase this value, it increases the influence of points far apart on each other, and the resulting model becomes smoother. It's like broadening the brush strokes in a painting. less detail, more overall smoothness. I see length_scale as a control knob for smoothness. A higher value means points far apart strongly influence each other, resulting in a smoother prediction curve. Think of it like drawing a line through many points. A large length_scale makes the line smoother, while a small one follows the points more closely. Makes sense? The alpha parameter is like a blend dial. It mixes two kernel types, squared exponential and Matern. As alpha increases, the blend shifts more toward the squared exponential kernel, making the model smoother. A small alpha shifts the blend towards Matern, emphasizing local data. So, where do you want to be on the smoothness spectrum? These bounds set limits on how high or low the length_scale value can go during optimization. 1E5 is a wide range, allowing the optimization process to explore many different levels of smoothness. It's like providing a search space for the optimal length_scale. This is the core question. It's asking you to assess the impact of the rational quadratic kernel's parameters on model behavior. You will need to understand how changing each parameter affects the model's predictions. Let's get started. I see length_scale as the dial controlling smoothness. A bigger length_scale means points farther apart strongly influence each other, creating a smoother curve. Think of it like connecting the dots with a really flexible rubber band. The further apart the dots, the smoother the curve. This parameter, alpha, acts like a switch between two types of curves. As alpha gets really big, the curve becomes like a squared exponential kernel, very smooth and predictable. But as alpha decreases, it behaves more like a Matern kernel that prioritizes nearby data points, leading to a more irregular curve. I think of it as a blend between two personalities. These bounds set the limits for length_scale. They're like fences around a playground, keeping length_scale within a certain range during calculations. 1E5 means length_scale can be as small as 0.00001 or as large as 100,000. This lets length_scale explore widely. This quiz question tests your understanding of how the parameters in a fancy math tool, specifically the Gaussian process regressor with a rational quadratic kernel, fancy words for a method that predicts stuff, affect the results. We're using a technique called Gaussian process regression that uses a special mathematical tool called a kernel to predict things. We're focusing on the rational quadratic kernel, which has some cool parameters to adjust. This phrase simply introduces the topic. We're going to explore how changing the parameters of the rational quadratic kernel affects the model it produces. Think of it like adjusting the knobs on a sound system. Each knob does something different to the overall sound. This is the core question of the quiz. We're asked to analyze how three parameters, lengthscale, alpha, and lengthscalebounds, influence a Gaussian process regression model using the rational quadratic kernel. Each parameter plays a distinct role in shaping the model's behavior and prediction accuracy. This statement discusses lengthscalebounds. These bounds define the minimum and maximum values allowed for lengthscale during the model training process. The range, 1E5 to 1E5, is incredibly wide, allowing the model to explore a very large space of possible lengthscale values to find the optimal one. Think of it like setting the maximum and minimum volume levels of an amplifier. A wide range means the model has lots of flexibility to adjust the influence of individual data points and the overall smoothness. Here, we examine the impact of the parameter alpha. The rational quadratic kernel acts as a bridge between two other kernels, the squared exponential and the Matern kernel. As we increase alpha, the rational quadratic kernel behaves increasingly similar to the squared exponential kernel. It's like a dimmer switch. A higher setting, larger alpha, brings us closer to one extreme, the squared exponential kernel. This option focuses on the relationship between alpha and the model's sensitivity to nearby data points. I find it helpful to visualize this. As we decrease alpha, the rational quadratic kernel shifts more towards the behavior of a Matern kernel, which tends to give more weight to nearby data points. This means local data will have more of an impact on the model's predictions. Think of it like a spotlight. A smaller alpha focuses the spotlight, highlighting nearby data. This simply indicates that multiple options might be correct in this multiple-choice question. We see this parameter controls how smooth the model is. A larger length underscore scale means points farther apart influence each other more, resulting in a smoother prediction. Think of it like this. A large length underscore scale is like drawing a smooth curve through your data points, while a small length underscore scale emphasizes the wiggles and bumps. This parameter determines how much the rational quadratic kernel behaves like a squared exponential kernel. As alpha gets really big, it becomes almost identical to a squared exponential kernel. A smaller alpha means it'll act more like a Matern kernel, which focuses more on nearby data points. It's like a dial. At one end, you've got smooth predictions, and at the other, you prioritize local details. These values set the limits for the length underscore scale parameter during optimization. The example, 1e5, means the length underscore scale can range from a very small value, 0.00001, to a very large value, 100,000. Think of it as giving the algorithm a search space for the optimal length underscore scale. In short, this section summarizes the effects of varying each parameter in the rational quadratic kernel on the model's behavior. Each bullet point describes a specific impact. Let's examine each effect individually for better understanding.